Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is the path with maximum probability. So you will be given an undirected graph, and it will be a weighted graph, and it will be consisting of n nodes, and the nodes will be indexed on the base of zero based indexing, and there will be one edges list that will be given to you, and each entry in this list represents uh, the first node and the second node a particular edge is connecting. Okay, so for example, if at ith index there is one entry in the edges list a comma b, then it indicates that there is an directed edge connecting nodes a and b. Okay, so the edges will not be directed, so it can be both ways, from a to b and b to a. Okay, with the probability of success of traversing that particular edge will be represented by another list that will be given to you, and or array you can say. It will be success probability array. So given two nodes start and end, you have to find the path with the maximum probability of success. Okay, so you will be given a value of the starting node and the ending node, and you have to tell what is the maximum probability path you can take to go from start node to the end node, and you have to return its the success probability that you will be finding, the maximum success probability path and its success probability. Okay, if there is no path from start to end, then you will be returning 0, saying that okay, the possibility of reaching from start to end is 0. Okay, and your answer will be accepted it if it differs from the correct answer by at most this much amount. Okay, 1e 10, it's like 10 raised to power minus 5. Okay, so you should be keeping in mind this much, approximation is allowed here. Okay, so for example, if you take the very first example that they have provided, so if you want to consider it as your input, so the starting and the ending node were given to be 0 and 2. Okay, so this is your start node. Okay, and this is your end node. So from start to end, there is one of the path is this, of having probability zero point 0.2. There is a direct edge between the start and the end node. Okay, this was one path. Another path that you could have taken is this one, starting from 0 going to 1 and then going to from 1 to 2. Okay, so what is the net probability here? The net probability will, first of all, you should be considering going from one edge to one traversing one edge, going from one node to another, separate event or independent event. So and you will be having a series of independent events in a path. By independent event I means traversing a edge. So your net probability will be zero point 0.5 into zero point 0.5. Okay, so you should be multiplying your probabilities because each edge traversal represents a independent event. So this much will be your net probability. Okay, and in this one it was 0 0.2, so answer will be obviously 0. And the greater probability one, so the 0.21 is the lesser probability one, and this is having higher probability. So as you can see, this will be your answer. Okay, so you need to keep in mind that you should be considering the path with higher probability of reaching the destination from start to end node basically. Okay, so this is what you have to return, the higher probability. Okay, so it is also mentioned in the explanation, there were two paths from start to end having a probability of 0.2 and zero point 0.5 into zero point 0.5, which is 0.25. Okay, so you should be returning 0.25. So I hope what you are now clear with what you have to return in the problem statement and while solving the problem. And before thinking of an approach, let's have a quick look at the constraints also. So according to the constraints, the number of nodes will be varying uh, in the order of 10 raised to power 4, and since it's a zero based indexing, so the node values will be from 0 to n excluded. Okay, and start and end will never be equal, and then the entries in the edges list that will be given to you will be falling within the valid node value range. Okay, and even in the entries this will be the case that the two vertices that a particular edge is connecting, or the nodes that a edge is connecting, will never be the same. So a will never be equal to b. So then it's mentioned that the length of the success probability uh, array that will be given to you and the edges list that will be given to you will be equal, since you have to take the probabilities of edges, so then that should be equal obviously, and that would be of range 2 into 10 raised to power 4. Okay, and success probability will be either 0, lying between two values, zeros and 1, as it is the case with the probabilities anyways. So then there is at most one edge between every two nodes, so there will not be multiple edges between two nodes, so this kind of situation will not be arising. uh, if there is this is one edge, let's not consider it as a directed edge, and this is another edge, so this kind of situation will not be there. There will be only at most one edge. Okay, one edge only between a pair of nodes. Okay, so these are the constraints. I hope everything is clear to you. Now let's try to think of an approach. So the very first approach that came to my mind while after reading this problem statement and seeing the constraints was that we can use algorithm. Basically, I was familiar with this algorithm. If you are new to this one, then link for this particular algorithms article on it will be provided in the description box. Anyways, I will also be explaining it in the video as we have implemented this algorithm for the solution part. So it is single source shortest path. So single source shortest path, or you can say Dijkstra algorithm. Pardon me if some spelling is incorrect. And yeah, this will be the algorithm that you will be using, Dijkstra algorithm, and a link of this particular article, uh, algos article, will be provided in the description box. Okay, you can definitely check this out if you are not familiar with it. Anyways, what happens in this algorithm is, let's take a new slide for that. First of all, since we mentioned that single source shortest path, so from a single source, okay, let's consider this one as the source, and to all other nodes present in the graph. Okay, let's say there are some nodes present in the graph. Okay, so from this source to all other nodes, you will be having the shortest distance by the end this algorithm completes. Okay, so what you will be having is, you will be having a array like structure. Okay, so it will represent a distance of each node, from source. Okay, and initially, let's say the source is the 0th index, and there are n vertices represented by 0 based indexing, and the source is this one. Okay, so initially source's distance from itself will be 0. Okay, rest all the uh, vertices will be having a distance of infinity from the source. Okay, and then what you will be doing is you will be using a min heap. Okay, this is just to tell you how shortest path algorithm works. Okay, we will reverse it and we will find the maximum probability. So then you will be having a heap. Okay, since it is the shortest path, so we should be using a minimum heap. If you are not familiar with heap also, article link to this particular data structure will also be provided. Basically it helps you to give you always the minimum or the maximum element depending upon the kind of heap you are using. Okay, so eh, heap will be storing nodes based upon their distance from the source. So initially source was at 0 distance from itself, so heap was having only source value. Okay, source node. Then each time you will ask heap for a node, it will give you the node which is at present uh, minimum distance from the source. And then once you take this element out of the heap, then you will be exploring its neighbors. Okay, neighbors are the nodes that are connected to this particular node that you have taken out from the heap, and you will be seeing uh, whether there is some probability of reaching its neighbors via lesser distance. So for example, let's say this was 0 and this was 1. Initially once value in this distance from source node was set to infinity, and zero's value was 0 since it was the source. Okay, so now it happened like this, that the edge weight was, let's say, what should we take, let's say edge weight was 3. Okay, so from 0 distance node, the source plus 3 is obviously lesser than the infinity that is currently stored against 1. Okay, this particular value, so that's why we should be updating this infinity to 3. So this is what you have to do for every neighbor, and once there is a updation, then the node for which the updation is being done, you will add that node to the heap. Okay, and this thing will continue, keep continuing until and unless your heap is empty. Okay, once your heap becomes empty, it indicates that okay, you have find the shortest path from source to all of the nodes. Okay, so this is in nutshell what this track algorithm or the single source shortest path algorithm is. Please check the articles on the Dijkstra algorithm, whose link is provided in the description box if you are not familiar with it beforehand, and if you are having any difficulty in understanding it here. So assuming that you have now familiarized yourself with this particular algorithm, now we will be try to think that how we can apply this particular algorithm to our this specific problem. Okay, so here we were finding the shortest path. Okay, but there in the problem statement we have to find the maximum probability path. Okay, so the changes that will be there will be, first of all, instead of infinity, since we are dealing with the probabilities, so infinity is just a way of saying that we are not able to reach from source to these vertices as of now. So in terms of probability, we can say that from the start vertex to the all of the vertices, the probability of reaching them is 0. So we should be inserting zeros instead of infinities. This is one thing that you have to keep in mind. And since you are already at the source, starting from the source or the start node, so probability of reaching from source to itself is 1. Okay, so that's why instead of 0 it will be 1. Okay, all these entries will be 0 initially, saying that there is no chance of reaching from source to these particular vertices. Okay, so this is what the initialization part tweak will be there. And the next thing will be, instead of min heap, since we have to deal with the maximum probability, so we should be using maximum heap. Okay, maximum in terms of probability each node is having to be reached from source. Okay, maximum in terms of this probability, and rest everything will be taken care of by the algorithm that we have just discussed. Okay, these will be few changes or few tweaks that we have to do in this algorithm. And now let's quickly see how we have implemented this algorithm with the tweaks that we have just discussed. Okay, and and the updation logic will also be changing. It is pretty obvious that since we are wanting maximum probability, so if this value is greater than the current values will be obviously zeros. Okay, so only then you will be updating and inserting the node into the maximum heap. Okay, so let's see the implementation, and the approach will be more clear to you in the implementation part. So this is the implementation. Let me take another slide and copy it there. So I hope it's visible enough for you, and we if can also zoom in a little bit, and we can scroll it while I will be explaining you the code. And let's break this into parts. I hope now it should be clear enough. Okay, and let's have a quick discussion on the implementation. Yeah, I think this should be fine now. So let's, yeah, this much size is sufficient so that it should not be overlapping, and let's remove this toolbar also. So what we are doing here is, these will be the inputs that will be given to you: the edges list, their success probabilities of the corresponding edges in the edges list, the start node and the end node. Okay, so you should be first of all having a graph with you representing these, how these edges are connected. So it will be like this: a node is can be connected to a number of other nodes. Okay, so each of these connections will be stored in a list. Okay, this list, and each entry in this list will be a pair. The first entry in this pair will be the probability of reaching, or the probability of this edge. Okay, this will be the first entry, and since probability are in double, so we have taken a double value. And then the second thing will be the value of that node. If this node's value is, let's say, y, then this will be uh, that particular part in the pair where node's value will be there. Okay, and it will be probability. So I hope you are clear with the structure of the graph, and we will be making this list for each of the nodes that is having some connections. And then, as we talked that in this try algorithm we will be needing a max heap. So we have used a heap that will be given you maximum probability node currently present in the heap. Probability in terms of, so probability, this is important that you keep this in mind. Probability in terms of uh, reaching, probability of reaching from source to that node. Okay, from source to a particular node. Higher the probability, the more likely will be the chances of that node to be selected from the heap, while you will be uh, querying doing a query in the heap to give you the maximum probability node, okay, which is having the highest probability of being reached from source. Okay, and it will also be a pair. First entry will be the probability of each node, and the second entry will be that node's value. Okay, and since we were using a max heap in terms of probability, so the first value was probability, so that's why we have sorted in descending order in terms of probability. Okay, so I think the data structures that we will be using for this particular algorithm and their structure is clear to you. Now let's proceed with the algorithm. Okay, so the first part will be to build the graph. Okay, so graph will be built by these two inputs, the edges array and the success probability array. And since they were mentioned to be of equal size, so we have used the size variable to take length of one of these arrays, and from 0th index to the very last index we are traversing these. So this is the probability of the current edge. Okay, this is the first node and the second node. So situation is like this: the first node is connected by an undirected edge to the second node. Okay, which is, by the way, what the array current entry in the edges array is representing. Okay, so for each node we talked about that would be wanting to have a list, okay, which represents all the nodes connected to a particular node and the probabilities of that particular edge. Okay, so if we are seeing these nodes for the very first time, then their list should be present in the map, so we are adding that. Then here what we are doing is we are adding the first node in the lists of the second node and vice versa. Okay, with the probability that will be for the current edge. And once we have done all of this, you will be having a graph that is representing the whole scenario. Okay, all the edges connections between the nodes and their corresponding probabilities. So then once we have everything ready, then we will be starting from the very first node, which is the source node. Okay, and there will be one array, as we talked about, will be initialized from source probability. Okay, probability of reaching a node from the source. All of the nodes will be having zero probability except the source itself, because probability of reaching from source to source is for sure 1. Okay, then you will be adding the current value corresponding to the source node, its probability of reaching from it reaching to itself. Okay, and its value. So a pair will always be inserted in your heap, and heap is managed according to this first entry in the pair. Okay, as it's observable here also. Then you will be picking the maximum probability node in terms of it being reached from source, which is present in the heap right now, and this whole procedure will be continuing till the heap does not becomes empty. Okay, so then you will be seeing, are there any neighbors of the current node? taken out from the heap. Okay, if there are no neighbors, then you will continue with the procedure and you will take another node out of the heap. And if there are some neighbors, then you will be visiting those neighbors. Okay, and they will be visited by getting the value from the graph. Okay, by the getting that list from the graph that is containing the neighbors of the current node. Okay, then you will be initializing uh, neighbor probability. Okay, which will be by given by the current entry in the list that will be returned by the graph. And then neighbors node value will also be extracted from the pair that you have just taken from the list. Okay, the pair is this neighbor pair. Okay, and then new probability will be calculated. What will be the new probability? The current node's probability to be reached from source multiplied by the neighbor's probability to be reached from current node. Okay, so if this probability is higher than the probability that is being stored against the neighboring node in this from source this probability array, then you will do a updation. Okay, here updation will be done. Okay, and if updation is being done, then once you have done the updation, you will insert the node also in the heap for which updation is being done. Okay, and this thing will continue until your heap becomes empty. Once your heap becomes empty, you will be having this particular in this particular array, and this array I am talking about. In this particular array, the distance of all the nodes, minimum distance of all the nodes possible from the source will be present, and you have to just return the minimum distance from source node to the end node, and this will be your result. Okay, so this is how the algorithm implementation will be done with few tweaks. Okay, and if we talk about the complexity, let me erase something so that there is enough space. So time complexity wise, see, the determining factor for time complexity here is the insertion and deletion of values from this heap that you are using, or this priority queue that you are using. So these are the determining factors. Okay, and these ones, this particular line. Okay, and if there are let's say e edges, then the e is the number of edges, the whole time complexity will be e into log of v. Since each of these operations, these two operations and this one also, if you want to consider it also, this particular one, each of these operations will take log of v, where v is the number of vertices, because it is the complexity of the heap, uh, push and pop operations in a way, and it will be done order of edges number of times, because uh, in a way you can say that e is the number of edges that can be incident upon a particular node. So it will be of order e. So log v operations will be done order of e number of times, so therefore the whole time complexity will be e log of v. Okay, and space complexity wise, see, uh, we were forming this map. How many entries can be there in this map? Order of e, the number of edges. Okay, and then we were using some space here. Okay, uh, for the vertices. So it is equal to the number of vertices or number of the nodes. Okay, so order of e plus v will be the space complexity. So these will be the complexities, and this is the approach. If you are still having any doubts or any queries in general, then you may ask them in the comment section. And I really hope this solution walkthrough added some value to your journey of honing your DSA skills. And keep solving more and more problems. And I will be seeing you in the next video. Thank you for watching.